Right now, in every direction you could ever travel beyond this planet, the universe sits at a temperature of 2.725 Kelvin. That is less than 3 degrees above the coldest condition that physics allows. Not the cold of a winter night, not the cold of Antarctica. Something so far beyond any cold you have ever felt that the comparison barely holds. Scientists have measured this temperature with extraordinary precision, confirmed by 3 generations of space-based instruments, most recently the Planck satellite operated by the European Space Agency. It is colder than liquid helium, 28 times colder than liquid nitrogen, 68 times colder than the lowest temperature ever recorded on the surface of the Earth. And it does not exist in isolated pockets. It fills everything, stretching across hundreds of millions of light years in every direction. For most of human history, nobody understood what that cold was, where it came from, or what it meant. Then, in 1964, 2 engineers at a telephone laboratory in New Jersey stumbled onto the faintest signal in the history of science and changed everything. What they found was the last light of the Big Bang itself, cooled by 14 billion years of cosmic expansion into something almost indistinguishable from silence. And buried inside it was a truth about the universe that most people have never been told. We will trace that signal to its source, measure the full scale of what it reveals, and follow the cold all the way to the end of time. If this is the kind of journey you want to take, subscribe and leave a like. It means more than you might think. The cold does not surround our warmth. It is everything else. And the story of how we came to understand that is one of the most remarkable in science. Everyone knows space is cold. Ask almost anyone, and the answer arrives without a moment's hesitation. Cold, empty, lifeless, freezing. It is one of those facts that feels so thoroughly settled, so confirmed by every documentary and classroom and piece of popular culture you have ever encountered, that questioning it seems almost beside the point. You already know. Space is cold. And that certainty is exactly where the problem begins. Not because the answer is wrong. It is not wrong, not exactly. But the question almost nobody thinks to ask, the question underneath the obvious one, is not how cold space is. It is how much of the universe is cold. What fraction of everything that exists sits at or near the absolute floor of what physics allows? How long that has been true? How long it will continue to be true? And what it actually means that you are here, right now, warm enough to be thinking about it. That question has a real answer. It is not vague. It does not dissolve into philosophy. It is a matter of physics and geometry and deep time. And when you follow it honestly all the way to the end, what you find is not reassuring, but it is one of the most clarifying things you will ever sit with. Here is the argument this video is going to make, stated as plainly as it can be. Warmth is not the natural state of the cosmos. It is not the background condition against which cold appears as an exception. It is the other way around. Warmth, the specific, narrow, almost improbably precise thermal range that makes liquid water possible and sustains the chemistry of living things, is a deviation, a local, temporary, vanishingly rare departure from a rule that governs nearly everything that exists. Cold is not the background. Cold is the thing itself. That is not a metaphor. It is not a dramatic flourish designed to make space sound more frightening than it is. It is what the measurements say once you take the full scale of the universe seriously and do the arithmetic without flinching. And this video will do that arithmetic. It will follow the physics of heat all the way down to the foundations, trace the origin of the universe's thermal baseline across nearly 14 billion years of cosmic history, survey the hot exceptions, the stars and the fires and the briefly glowing things, and then hold them up against the cold that surrounds them and measure how they compare. By the time that accounting is complete, the universe will look different to you. Not smaller, not simply more frightening, more precisely understood. And that precision carries a weight that no amount of general wonder can quite match. So set aside what you think you already know. The easy answer is not wrong. but it is the smallest version of the truth. The larger version is what we are here to find. It begins with a question that sounds simple and turns out not to be at all. What is cold, actually? The word describes an experience so universal, so immediately physical, that it feels less like a concept and more like a basic feature of the world. You step outside on a winter morning and the cold is just there, pressing, immediate, taking the warmth out of your hands and face and chest. It does not feel like an absence. It feels like something arriving. That feeling is misleading. And understanding exactly how it misleads you is the first step toward understanding what space is really like. When you feel cold, here is what is actually happening. Your body maintains a core temperature of approximately 37 degrees Celsius through continuous metabolic processes. The air around you on a cold day is substantially cooler, perhaps -5, perhaps -10. The molecules of nitrogen and oxygen that make up that air are moving more slowly than the molecules in your skin. When they collide with you, and they do, billions of times per second across every exposed surface, they carry less energy away than warmer molecules would. Your body's thermal energy flows outward into the cooler air. Your nerve endings register the loss. Your brain calls it cold. But notice what is happening in that sequence. The cold is not a thing that is entering you from outside. Cold is a direction. It is the direction energy moves when it flows from somewhere warmer towards somewhere cooler. What you are experiencing is heat leaving, not cold arriving. The distinction sounds like a fine philosophical point. It is actually the difference between understanding temperature as something the world possesses and understanding it as something that describes how energy behaves between things. Temperature, stated formally, is a measure of the average kinetic energy of the particles in a substance. Faster moving particles mean higher temperature. Slower moving particles mean lower temperature. When two substances are in contact and one is hotter than the other, energy transfers from the faster moving molecules to the slower moving ones, collision by collision, particle by particle, until both reach the same average speed. That shared endpoint is thermal equilibrium, and the temperature at which it settles is the result of that exchange. All of this requires something that is easy to take for granted. It requires matter. It requires particles that can move, collide, and pass energy back and forth. Temperature is not a property of emptiness. It is a property of stuff. Ask what temperature a perfect vacuum is, and you have asked a question that classical thermodynamics cannot cleanly answer, because there is nothing there for the concept to attach to. This is where the intuition built by a lifetime inside an atmosphere starts to break down. On Earth, air is everywhere. It fills every space you inhabit, presses against every surface, carries heat from warm objects to cool ones and back again. The idea that temperature is a property of the surrounding environment is so relentlessly reinforced by daily experience that it feels like a law of nature. It is not. It is a consequence of living on a planet wrapped in a dense gaseous shell. Remove the shell, and the rules change in ways the nervous system has no apparatus to anticipate. Now consider what happens as you cool a substance down, really down, far past anything encountered in ordinary experience. As you extract energy from it, its molecules slow. The temperature drops. You can continue this process, extracting more energy, watching the temperature fall further, and there is no obvious point at which you would expect it to stop. But there is a floor, a point below which no further extraction is possible. That point is 0 Kelvin. 0 Kelvin, minus 273.15 degrees Celsius, minus 459.67 degrees Fahrenheit. Absolute zero. At absolute zero, the thermal motion of particles has reached its minimum permitted state. This is not merely a very low temperature in the way that minus 80 degrees is a very low temperature. It is a boundary, the point at which the concept of extracting further thermal energy from a system ceases to have physical meaning. Every particle retains a small irreducible energy called zero-point energy because quantum mechanics forbids complete stillness, even at the coldest possible condition. But no thermal process can go below it. No heat pump, no cryogenic apparatus, no physical mechanism of any kind can cross that line. The third law of thermodynamics makes this explicit. Reaching absolute zero is impossible, not difficult, not beyond current technology, impossible as a matter of principle. To reach it exactly would require an infinite sequence of cooling steps, each one extracting a smaller increment of energy than the last, converging toward the floor but never landing. The universe has never achieved it. No laboratory has achieved it. No process in nature produces it. Absolute zero is the wall at the bottom of the thermometer that nothing has ever touched. Think about what that means. The coldest achievable condition in the entire universe has never been reached by anything, anywhere, at any point in the 14 billion years of cosmic history we can observe. The floor exists, it is precisely defined, and it remains untouched. The coldest temperatures ever produced by human beings have come from physics laboratories using techniques that took decades to refine. Laser cooling, magnetic trapping, evaporative cooling, bringing tiny clouds of atoms to within billionths of a degree of absolute zero. Not thousandths, not millionths, billionths. And still, the floor was not reached. Still, the molecules retained their last irreducible flicker of motion. Still, absolute zero held. This is the scale of cold the universe operates in. The cosmic microwave background, the ancient radiation that fills every cubic meter of observable space, sits at 2.725 Kelvin, 2.725 degrees above absolute zero. On a thermometer running from the floor to the surface of the sun, that number sits so close to the bottom that you could not see the gap with the naked eye. Hold that against the benchmarks of cold that humans actually use. Liquid nitrogen, used to flash freeze biological material and shatter metal in industrial settings, boils at 77 Kelvin. The cosmic background temperature is roughly 28 times colder than that. Liquid helium, the coldest commonly available cryogenic fluid, boils at 4.2 Kelvin. The background temperature of the universe is colder still, and the coldest temperature ever recorded naturally on the surface of this planet, minus 89.2 degrees Celsius at the Soviet Vostok station in Antarctica in July of 1983, translates to approximately 184 Kelvin. Roughly 68 times warmer than the cosmic baseline. What passes for extreme cold in human experience is, by cosmic standards, barely registering. But here is the essential thing about that number, 2.725 Kelvin. And this precision matters. It is not the temperature of empty space the way 20 degrees is the temperature of a comfortable room. Space does not have a temperature in that classical sense, because space is not filled with any substance dense enough to possess one. True deep space contains so little matter that applying the word temperature to the void itself requires care. What 2.725 Kelvin actually describes is this: it is the equilibrium temperature that any object will eventually reach if you place it in deep space, far from any star or local radiation source, and leave it alone long enough. As the object radiates its own thermal energy outward, it cools. As it cools, the rate at which it sheds energy decreases. At some point, the energy it emits exactly matches the faint energy arriving from the cosmic microwave background, ancient radiation flowing in from every direction with extraordinary uniformity. At that point, cooling stops. The object has reached 2.725 Kelvin. Not because the vacuum around it is that temperature in a classical sense, but because the oldest light in existence arrives from every direction at an intensity corresponding to that temperature, and nothing in nature can cool below the equilibrium that light defines, 2.725. Kelvin is not the temperature of nothing, it is the temperature of the last light, the afterglow of creation, stretched and cooled by nearly 14 billion years of cosmic expansion into microwaves so faint that no biological sense could ever detect them, and yet present and real, and arriving from every direction at every moment. Where that light came from, what it encodes, and what it reveals about the structure and fate of everything, that is the story waiting ahead. And it begins not in the cold, but in the most violent heat the universe has ever produced. To understand why space behaves the way it does thermally, you need to understand something that most people learned once, in passing, and never thought about again. Heat does not move through the universe in one way. It moves in three entirely different ways, through three entirely different mechanisms. And the reason space is so alien, the reason the rules you have lived by your entire life stop working the moment you leave the atmosphere, is that two of those three mechanisms vanish completely in a vacuum. They do not become less effective. They do not slow down or weaken. They cease to operate at all. And what remains determines everything about how temperature behaves beyond Earth. The first mechanism is conduction. Place your hand flat on a metal countertop and feel the cold move into your palm. What you are feeling is molecules in the metal, which are moving more slowly than the molecules in your warmer skin, accepting energy from your hand through direct physical contact. The vibration passes from particle to particle across the boundary between your skin and the surface. This is conduction, heat transferred by direct molecular contact between two objects touching each other. Conduction is why metal feels colder than wood at the same temperature. The metal is not actually colder. Both surfaces sit at room temperature, but metal conducts heat away from your skin far more efficiently than wood does, so the energy leaves your hand faster, and your nervous system interprets faster energy loss as lower temperature. You are not measuring the temperature of the material. You are measuring how quickly it is draining you. Conduction requires physical contact. It requires two objects pressing against each other, molecule to molecule across a shared boundary. In the vacuum of space, that contact does not exist. There is nothing pressing against you. There is nothing to touch. Conduction, as a mechanism of heat transfer, simply does not apply. The second mechanism is convection. Heat a pan of water on a stove and watch what happens. The water near the bottom warms first, becomes less dense, and rises. Cooler water near the surface sinks to take its place. A circulation loop develops, warm fluid rising, cool fluid descending, heat carried through the bulk movement of the fluid itself. This is convection, and it operates not just in water, but in any fluid system. The atmosphere, the oceans, the interior of the Earth, the outer layers of the sun. Convection is why a breeze feels cooling, even on a day when the air temperature is the same as your skin. Moving air carries warm molecules away from your body and replaces them with cooler ones, accelerating heat loss. It is why fans work. It is why wind chill exists. It is why the atmosphere of Earth acts as a vast thermal mixing bowl, constantly redistributing heat from the equator toward the poles, from the surface upward, from warm regions into cool ones. Convection requires a fluid. It requires matter that can flow, circulate, and carry energy from one place to another in bulk. In space, there is no fluid. There is no medium to circulate. Convection ceases to exist as surely as conduction does. What remains is radiation. Every object with a temperature above absolute zero emits electromagnetic radiation, not as a special property of certain materials or a consequence of particular conditions, but as an inescapable physical fact that applies to everything, everywhere, at all times. Your body is emitting infrared radiation right now. The walls of the room around you are emitting it. The ground beneath you, the clouds above you, every object you have ever touched or seen is constantly broadcasting energy outward in the form of photons, at a rate and in a spectrum determined entirely by its temperature. This is thermal radiation, and it obeys a precise mathematical relationship worked out independently by Joseph Stephan and Ludwig Boltzmann in the 19th century. The total energy a surface emits per unit area scales with the fourth power of its temperature. Double the temperature and the radiated power increases not by a factor of 2, but by a factor of 16. Halve the temperature and the power drops to 1/16. Temperature governs radiation with extraordinary sensitivity. Crucially, and this is the property that makes radiation the only game in space, it requires no medium. Electromagnetic radiation travels through a perfect vacuum, as naturally as sound travels through air, crossing empty space at the speed of light, without losing a single photon to friction or absorption along the way. The sunlight reaching your face right now has crossed approximately 150 million kilometers of essentially empty space to get there. It did not need anything to travel through. The void offered no resistance and no assistance. It simply passed. This is the thermal reality of space in a single sentence. The only mechanism by which heat moves in a vacuum is radiation, and the temperature of any object in space is therefore determined entirely by the balance between the radiation it absorbs and the radiation it emits. Nothing else. No conduction, no convection. Just the incoming flux of photons from whatever sources happen to be shining, and the outgoing flux of photons from the object itself, and the equilibrium point where those two quantities match. That balance is called thermal equilibrium, and in space it can produce conditions of extraordinary violence separated by extraordinarily small distances. Imagine yourself on a spacewalk in low Earth orbit. The sun is shining, not filtered through an atmosphere, not softened by cloud cover or scattering, but direct and unmediated. Solar radiation arrives at approximately 1,360 watts per square meter. Every square meter of surface facing the sun receives that energy continuously, with nothing to moderate it. On the sunlit side of your suit, that radiation pours in and heats the surface. Without active thermal management, temperatures on the illuminated side of a spacesuit can climb past 120 degrees Celsius. Hotter than boiling water. Hot enough to cause severe burns on unprotected skin within minutes. Now consider the opposite side of that same suit, the side facing away from the sun. No solar radiation reaches it. It is not merely in shade the way the shaded side of a building on a summer afternoon is in shade, where air temperature is roughly the same everywhere, and shade offers only a modest relief. In orbit, the shadowed side of your body faces the void. No air surrounds it. No molecules conduct warmth toward it. No convection circulates heat from the sunny side around. The shadowed surface radiates its own thermal energy outward into the darkness and receives almost nothing in return. The temperature drops. In the permanent shadow of deep space, surface temperatures fall to -170 degrees Celsius or lower. That is a difference of nearly 300 degrees from one side of a human body to the other. Not across a vast distance, not separated by any material or barrier, across the width of a person. Both sides exist simultaneously, within arm's reach of each other, in the same location in orbit, separated only by the presence or absence of a direct line to the sun. On Earth, that kind of temperature difference is physically impossible at that scale. The atmosphere prevents it. Air conducts heat from the warm side toward the cool side. Convection stirs the boundary layer and smooths the gradient. Wind carries warmth into shadow. Even on the most extreme terrestrial day, the temperature difference between standing in direct sunlight and stepping into shade is a few degrees at most. The atmosphere is an enormous thermal buffer, relentlessly equalizing, relentlessly moderating. In space, the buffer is gone, and what replaces it is nothing. This is why the engineering of every spacecraft ever built has had to grapple with a problem that sounds almost paradoxical. How do you simultaneously prevent something from freezing and prevent it from overheating when the same object occupies both conditions at once? The International Space Station orbits Earth once every 90 minutes, cycling from full sunlight to complete shadow and back again 16 times every day. Each transition is a thermal shock. The station's exterior hardware must survive temperature swings of over 200 degrees Celsius on every orbit. Exposed metal surfaces on the sunlit side reach temperatures that would melt solder. Components in permanent shadow must be kept above their minimum operating temperatures using electric heaters, or their batteries fail, their fuel lines freeze, and their seals crack. Managing this is not a secondary concern in the design of the station. It is one of its primary engineering challenges. The station carries roughly 2,500 square feet of radiator panels, enormous flat surfaces kept permanently angled away from the sun, whose sole purpose is to reject excess heat into the void as infrared radiation. Without them, the electrical systems, the computers, the metabolic output of 6 human beings, and the absorbed solar energy would accumulate inside a sealed metal container with no way out. The interior temperature would climb until the station became uninhabitable. At the same time, shadowed components on the station's exterior are wrapped in multi-layer insulation and connected to electric heaters that run continuously. The engineering is not keeping the station warm against the cold of space. It is managing a simultaneous battle on 2 fronts, shedding heat from one part of the structure while adding it to another, all at once, on every orbit, indefinitely. The astronauts who have worked outside that station on spacewalks carry this problem on their bodies. The suits they wear are not simply insulated garments. They are miniature thermal control systems with water-cooled undergarments, reflective outer layers, and ventilation circuits that manage the temperature of the person inside, regardless of which way the suit happens to be facing. The suit must keep a human being alive within a narrow thermal band, while one side of it bakes and the other side freezes simultaneously, with no atmospheric buffer between the two conditions. This is what the absence of conduction and convection actually means in practice. It does not mean space is uniformly cold. It means space is indifferent. It offers no moderation, no buffering, no smoothing of extremes. Whatever radiation arrives, heats. Whatever faces the void, cools. The gradient between those two states can be brutal, and it can exist across a distance you could cross in a single step. The Moon demonstrates this at a scale you can hold in your mind without engineering jargon getting in the way. Its story is next. The Moon is the closest thing we have to a controlled experiment in planetary thermal physics. It sits at roughly the same distance from the Sun as the Earth. It receives roughly the same intensity of solar radiation. It is made of rock and dust, not so different in composition from the ground beneath your feet. And yet the temperatures it experiences would kill you in minutes, not because of anything exotic about its chemistry or its distance from the Sun, but because of one single absence. It has no atmosphere. That is the entire explanation. No air, no molecules to conduct heat across its surface, no fluid to redistribute warmth through convection, no blanket of gas to moderate the difference between what the Sun illuminates and what the Sun ignores. Just rock, vacuum, and radiation. The same rules that govern all of space, applied to a surface large enough to observe clearly. During the lunar day, which lasts approximately 2 Earth weeks because the Moon rotates so slowly, the surface at the equator heats under direct, unfiltered sunlight. Temperatures climb to approximately 127 degrees Celsius, hotter than boiling water. The regolith, the loose, powdery surface material, absorbs solar energy with nothing to carry that heat away, nothing to mix it into a surrounding medium, nothing to soften the accumulation. It simply builds. Then the sun sets. The 2-week lunar night begins. The surface that was absorbing over a kilowatt of solar energy per square meter is now facing the void with nothing incoming to replace what it loses. It radiates its own heat outward into the darkness. The temperature drops and continues dropping until it reaches approximately minus 173 degrees Celsius. A swing of 300 degrees. The same rocks, the same dust, heated to temperatures that would boil water, then cooled to temperatures that would freeze carbon dioxide solid on every single rotation, driven entirely by whether the sun happens to be above or below the horizon. On Earth, the most extreme natural temperature swing between the hottest day and coldest night in the harshest desert environments reaches perhaps 50 to 60 degrees. The Moon swings 5 times further than that, without moderation, without anything to soften the transition. The atmosphere Earth takes for granted is performing a thermal service so profound that it is almost impossible to appreciate from inside it. The moment it is removed, this is what you get. The permanently shadowed craters near the lunar poles make the point even sharper. Their floors have not seen direct sunlight in billions of years, preserved in perpetual darkness by simple geometry. The Lunar Reconnaissance Orbiter has measured some of these regions as among the coldest surfaces in the solar system, approaching -250 degrees Celsius. Not the coldest in the universe, not close to the cosmic baseline, but the coldest surfaces measured anywhere in our local neighborhood of space, and they exist less than 250,000 miles away. The extreme cold is not a distant abstraction. It is geography. It is the consequence of a shadow. Here is what shadows in space are that they are not on Earth. A shadow on a warm afternoon is a mild relief, a few degrees cooler, barely perceptible if the air is warm. That gentleness exists because air fills the shadow. Molecules from the sunlit surroundings drift in, carrying thermal energy across the boundary. Warmth bleeds in from the edges. In space, a shadow is a thermal cliff. Step from sunlight into shadow on the lunar surface, and the radiation environment changes instantaneously and completely. No gradual transition. No molecules carrying residual warmth across the line. The boundary between illuminated and shadowed regolith can represent a temperature difference of hundreds of degrees across a distance you could step over. Not a gradient. A wall. This is what the moon teaches, stated plainly. Remove the atmosphere, and you do not simply make a world colder. You make it savage. You expose every surface to the raw arithmetic of radiation alone. Absorb what the sun provides, emit what physics demands, and let the difference be whatever it is, without anything standing in the way. Earth sits at the same distance from the sun. It receives the same solar flux. Its surface averages a comfortable 15 degrees Celsius because of the thin shell of gas wrapped around it, a shell that took billions of years to produce. The moon is not a distant warning. It is the nearest demonstration of what the universe's thermal rules look like when nothing stands in their way. And those rules, scaled up to the full size of the cosmos, produce something far more extreme than anything the lunar surface has ever seen. To understand that, you need to understand the number this video keeps returning to, the temperature that fills all of space, everywhere, in every direction, at every moment. That number has an origin, and the story of where it comes from is one of the most extraordinary in the history of science. 2.725 Kelvin. The number has come up several times already, used as a reference point, a floor, a baseline to measure other things against. But it deserves more than that. It deserves to be understood for what it actually is, because once you understand it fully, the thermal reality of the universe stops being an abstract scientific fact and becomes something you can feel the weight of. That number is not arbitrary. It is not a property of space the way the temperature of a room is a property of the air inside it. It is a measurement of something real and specific, ancient radiation that fills every cubic meter of the observable universe with extraordinary uniformity, arriving from every direction at every moment, carrying almost no energy per photon, but setting the lowest temperature any passive object in the cosmos can naturally reach. This radiation is called the cosmic microwave background, and it is the oldest light in existence. The precision of the measurement matters here. In 2009, physicist D.J. Fixson compiled the most careful determination yet made of the background temperature and arrived at 2.72548 Kelvin with an uncertainty of less than 6/10,000ths of a degree. This is not an approximation. The universe's thermal baseline is known to 5 significant figures. A signal this uniform, this consistent across the entire sky, this exactly described by the mathematics of thermal radiation from a perfect blackbody. This is not noise. This is a relic. Here is what that relic means for the thermal experience of the cosmos. Any object placed in deep space, shielded from starlight and every other local energy source, will radiate its own heat into the void. As it does, it cools. Its temperature falls toward the background level, but it cannot fall below it. The cosmic microwave background provides a minimum input, faint, uniform, arriving from all directions simultaneously, that prevents any natural cooling process from reaching absolute zero. The background is the floor. Nothing in the universe outside a laboratory can get below it through passive cooling alone. The universe has a minimum temperature. It is set not by any local condition or any particular object, but by radiation that permeates all of space equally, derived from an event that occurred nearly 14 billion years ago. The universe's coldest achievable natural condition is defined by its own history, and that history is written in the number itself. 2.725. Kelvin is what you get when you start with visible light at approximately 3000 Kelvin, the temperature of the early universe at the moment its first atoms formed, and stretch it by a factor of roughly 1100. That is how much the universe has expanded since that moment. Every photon released at that instant has had its wavelength stretched by that same factor, its energy drained by the same expansion of space, until light that once glowed a dim red has become microwave radiation, too long in wavelength for any biological sense to detect. The number is not just a temperature, it is a compression of cosmic history into a single measurement. It encodes how old the universe is, how much it has expanded, and how thoroughly the original heat of creation has been diluted. All of that in 5 significant figures. Now place the current number against what it will become. The universe continues to expand. As it does, the photons of the cosmic microwave background continue to stretch. Their wavelengths grow longer, their energies drop, the temperature falls. A universe twice its current size will have a background temperature of roughly 1.4 Kelvin. A universe 10 times larger will sit at about 0.3 Kelvin. The floor itself is descending, slowly, without pause, toward an asymptote it will approach but never reach. The universe is not in a stable thermal state. It is in a cooling state. It has been cooling since the moment of its creation and will continue to cool for as long as it exists. The 2.725 Kelvin you can measure today is a snapshot of a process already well advanced. The long, patient, irreversible dimming of the oldest light. The universe was once filled with visible light at every point. Every location in space glowed. There was no darkness anywhere, not because stars had not yet formed, but because the primordial plasma itself was luminous, radiating at thousands of degrees in every direction simultaneously. That era ended. The light cooled and stretched. What remains of it today is the microwave background, the last faint echo of a universe that was once a furnace. Understanding that transition fully means going back to the conditions that existed before the background radiation was even released, when the universe was young and hot and opaque in ways that have no parallel in anything that exists today. That is where the story goes next. 13.8 billion years ago, the universe did not exist, not in any form you could recognize, not as empty space waiting to be filled, not as a vast dark void primed for ignition. There was no space. There was no time. There was nothing. And then, in a moment that physics can approach, but not fully describe, everything began. What followed was not an explosion in the ordinary sense. It was not a detonation inside pre-existing space, the way a bomb goes off inside a room. It was an explosion of space itself, the fabric of reality erupting into existence and expanding outward, carrying with it densities of matter and energy so extreme that every number attached to that first instant sits beyond the reach of useful analogy. In the first fraction of a second, the entire observable universe, everything you can see through the most powerful telescope ever built, across 46.5 billion light-years in every direction, occupied a volume smaller than a single atom. The temperature in those first moments exceeded 10 trillion degrees. Every particle of matter and energy that would eventually become galaxies, stars, planets, oceans, and living organisms existed as a seething, undifferentiated plasma of almost unimaginable heat. That heat is where everything that follows begins, because the universe has been cooling ever since. In the first second, the temperature dropped from trillions of degrees to roughly 10 billion degrees. That sounds like catastrophic cooling, and by any ordinary measure it was. But 10 billion degrees is still hotter than the core of the most massive stars that exist today. The universe at 1 second old was a blinding plasma of protons, neutrons, electrons, photons, and neutrinos, all colliding with energies that would vaporize any structure that has ever existed in the modern cosmos. Matter and radiation were locked together in a violent embrace, exchanging energy continuously, keeping every component in step with every other. Between roughly 10 seconds and 20 minutes after the Big Bang, the temperature fell into a range where something remarkable became possible. The plasma had cooled just enough, to temperatures between roughly 1 billion and a few hundred million degrees, for protons and neutrons to begin binding together into atomic nuclei. Not atoms, not yet. Just nuclei. The simplest possible combinations first. A single proton to make hydrogen, a proton and a neutron fused together to make deuterium, 2 protons and 2 neutrons locked together to make helium-4. Trace amounts of lithium assembled from slightly more complex reactions. This window was brief. Once the temperature dropped below a few hundred million degrees, the particles no longer moved fast enough for fusion to occur. The window closed. The universe's first and only period of large-scale nuclear synthesis was over, in under 20 minutes. Every nucleus that would ever be produced by the Big Bang itself was already formed. Physicists Ralph Alpher and George Gamow worked out the basic framework of this process in the 1940s, predicting that the Big Bang should have produced hydrogen and helium in specific proportions determined by the temperature and density of the early universe at the moment fusion was possible. The ratio their calculations pointed to was approximately 75% hydrogen and 25% helium by mass, with trace amounts of deuterium and lithium. Observations of the oldest, most chemically primitive stars in the universe confirm that ratio with striking precision. The abundances of the lightest elements are a direct fossil of conditions that existed in the first 20 minutes of time. But the universe was still extraordinarily hot. For hundreds of thousands of years after those first nuclei formed, temperatures remained far too high for electrons to bind to them and complete the formation of neutral atoms. Above roughly 3000 Kelvin, any electron that approached a nucleus was immediately knocked free again by surrounding photons, which carried enough energy to ionize any atom that dared to form. The plasma state persisted. The universe remained a charged, churning medium, with no stable atomic structure anywhere within it. And the consequence of that for the thermal story of the universe is this: free electrons are phenomenally effective at scattering photons. Every time a photon encountered a free electron, it bounced off in a new direction. Light existed everywhere. The universe was filled with it, but it could travel almost no distance before deflecting off another electron and changing course. The universe was opaque, not dark, opaque. The distinction is important. Darkness is the absence of light. This was the opposite. Light saturating every point in space, unable to go anywhere, ricocheting endlessly through the charged fog. Every direction you could have looked was a wall of blazing, luminous plasma. Information could not travel. No structure could be seen across any meaningful distance. The cosmos was a furnace in every sense, hot, bright, sealed, and going nowhere. This state persisted for approximately 380,000 years. Think about that duration. 380,000 years of a universe so hot and so dense that light itself was imprisoned. Not slowed, not filtered, trapped. Every photon generated during that period was absorbed and re-emitted and deflected again and again before it could travel any significant distance. The universe was simultaneously the most luminous thing that has ever existed and invisible in every practical sense. Then the universe crossed a threshold. As the temperature dropped toward 3000 Kelvin, the photons surrounding each nucleus finally lost enough energy to stop ionizing whatever they touched. For the first time in cosmic history, an electron approaching a proton could complete its orbit without being knocked away. Neutral hydrogen atoms formed. Helium nuclei captured their electrons. In a transition that unfolded over tens of thousands of years, fast by cosmological standards, the universe went from a plasma of free charges to a gas of neutral atoms. The moment neutral atoms formed, the universe became transparent. It happened because neutral atoms simply do not scatter photons the way free electrons do. The interaction cross-section dropped precipitously. When the electrons disappeared into atoms, the fog lifted. The photons that had been trapped and ricocheting for nearly 400,000 years were released. All at once, in that cosmological sense of all at once, they were free to travel in straight lines in every direction for the first time in the history of everything. Physicists call this event recombination, a slightly misleading name since the electrons and nuclei had never actually been combined before. It was not recombination. It was combination for the first time, ever. The surface from which those photons were released is called the surface of last scattering. Every photon in the cosmic microwave background was emitted at that surface, at that moment, and has been traveling in a straight line ever since. When you detect the cosmic microwave background, when an instrument measures it because no eye can see it, you are receiving light that last interacted with matter 380,000 years after the Big Bang. You are looking, as directly as physics allows, at the universe as it existed when it was less than 0.03% of its current age. If you could have been present at the moment of recombination, somehow surviving, somehow observing, the sky in every direction would have glowed a deep, uniform red. Not the layered red of a sunset scattered by atmosphere. A flat, featureless, omnidirectional crimson extending to every horizon at once. The temperature was roughly 3000 Kelvin, the surface temperature of a cool red star. Every point in the universe was a source of light. There was no darkness in any direction. That glow has been traveling and cooling ever since. The universe has expanded by a factor of roughly 1100 since recombination. Every photon from that moment has had its wavelength stretched by that same factor, from the near-infrared deep into the microwave region of the spectrum, a region invisible to every biological eye that has ever existed. The temperature dropped from 3000 Kelvin to 2.725 Kelvin. The omnidirectional crimson glow became an omnidirectional microwave whisper, filling all of space, detectable only by purpose-built instruments. There is one more element of this story that must be addressed, because without it, the uniformity of the background radiation presents a problem with no obvious solution. The temperature of the cosmic microwave background is essentially the same in every direction, uniform to 1 part in 100,000 across the full sky. Photons arriving from opposite sides of the observable universe carry the same temperature, but those regions were separated by enormous distances at the time of recombination, far too far apart for light to have traveled between them since the Big Bang. They had no physical means of reaching thermal equilibrium with each other. So how are they the same temperature? This puzzle is called the horizon problem, and it troubled cosmologists for decades. The solution came in 1981, when physicist Alan Guth proposed that the universe underwent a period of extraordinarily rapid expansion, inflation, in the first tiny fraction of a second after the Big Bang. Not the gradual expansion that continues today, but something incomparably more extreme, an exponential stretching of space by a factor of at least 10 to the power of 26, occurring in roughly 10 to the power of minus 36 seconds. Before inflation, the regions that would eventually be separated by billions of light years were close enough to exchange energy and reach the same temperature. Inflation flung them apart instantaneously, preserving their thermal uniformity while placing them beyond any future possibility of communication. The uniformity of the cosmic microwave background is not a coincidence. It is a fossil of a shared thermal history that predates the expansion that separated those regions. Guth's proposal did something else. During inflation, quantum fluctuations, the inherent irreducible randomness of energy at the subatomic scale, were stretched from microscopic scales to cosmic ones. Tiny variations in energy density, each one smaller than an atom, became perturbations spanning millions of light years. These are the seeds of everything that came after: the filaments and voids of the cosmic web, the galaxy clusters, the galaxies themselves, and finally the stars and the planetary systems, and the one thin, warm shell of atmosphere where the temperature happens to permit liquid water. The cosmic microwave background preserves a snapshot of those density variations, frozen at the moment of recombination. The 1 part in 100,000 temperature fluctuations that modern satellites have mapped with extraordinary precision are the amplified imprint of quantum noise from the first moments of time, written across the full sky in the oldest light the universe will ever produce. The fire made the silence, and buried inside the silence is the blueprint for everything. Reading that blueprint required instruments that did not exist until the late 20th century, and scientists who were, in one celebrated case, not looking for any of this at all. In 1964, in a field in Holmdel, New Jersey, 2 engineers were trying to build a better antenna. That is the whole of their intention. No cosmology, no questions about the origin of the universe, no interest in the thermal history of creation. They wanted to reduce noise in a communication system, and they were losing a battle against a sound they could not explain. The antenna was a large, horn-shaped structure, originally built by Bell Telephone Laboratories for use with the early Telstar communication satellites. By the time Arno Penzias and Robert Wilson began using it for radio astronomy, the satellite program had moved on, and the horn was available for other work. The 2 men pointed it at the sky and began trying to map faint radio signals from the outer regions of the Milky Way. Before they could do that, they needed to account for every source of noise in the system, every stray signal, every instrument artifact, every contamination that might corrupt their measurements. This is where the story takes its famous turn. No matter what they did, there was a persistent hiss in the signal. It was faint, uniform, and impossible to eliminate. It did not vary with the time of day. It did not change with the season. It did not come preferentially from the plane of the Milky Way or from any known radio source. It came from every direction equally, with a constancy that made it deeply frustrating. Penzias and Wilson worked through every possible explanation methodically. They checked the antenna for loose connections. They recalibrated their equipment. They pointed the horn at the sky in every direction and found the same result each time. Then they looked inside the antenna itself. A pair of pigeons had nested in the horn. The birds had coated the interior with what Penzias later described, with characteristic understatement, as a white dielectric material. The 2 men climbed in, cleaned it out, removed the pigeons, and took their measurements again. The hiss remained, identical in every direction, constant across every frequency band they examined within the relevant range, corresponding, when they analyzed it carefully, to thermal radiation from a source at roughly 3.5 Kelvin, just a few degrees above absolute zero. They had no idea what it was. 40 miles away in Princeton, a group of physicists had independently arrived at a prediction. Robert Dicker had been thinking about cosmology and concluded that if the universe had begun in a hot, dense state, as the emerging framework of Big Bang theory proposed, then the heat from that era should still be detectable today as a faint background of thermal radiation. It would have cooled enormously as the universe expanded, but it should still be there, arriving uniformly from every direction at a temperature of perhaps a few Kelvin. Dicker and his colleagues, including the theorist Jim Peebles, were in the process of building their own antenna to search for exactly this signal. They never got to look. Word reached Princeton of what Penzias and Wilson had found. The connection was immediate. What the 2 Bell Labs engineers had been trying to eliminate for months, the persistent, inexplicable, omnidirectional hiss that survived every attempt at removal, including the eviction of nesting birds, was the remnant thermal radiation of the Big Bang itself, the oldest light in the universe. The photons released at recombination 380,000 years after the beginning of time stretched by 14 billion years of cosmic expansion into microwaves of such faint energy that two experienced radio astronomers had mistaken them for instrument noise. Penzias and Wilson published their measurement in 1965. Dickey and Peebles published the theoretical interpretation alongside it. The two papers appeared back-to-back in the same issue of the Astrophysical Journal, the detection and the explanation arriving simultaneously from two separate groups working 40 miles apart, one of whom had been looking for the signal and one of whom had not. Penzias and Wilson received the Nobel Prize in Physics in 1978. Dickey and Peebles were not included. That omission is a lasting point of discomfort in the history of the field, though Peebles would eventually receive his own Nobel Prize in 2019, in part for his foundational contributions to cosmology, including his early theoretical work on the background radiation. The initial measurement was crude by later standards, 3.5 Kelvin, with significant uncertainty, but the discovery itself was one of the most consequential in the history of science. It transformed the Big Bang from a compelling theoretical framework into an observationally confirmed fact. The universe had a hot beginning. The evidence was ringing in an antenna in New Jersey, and it had been there since before any human instrument existed to hear it. What followed was decades of increasingly precise measurement, a generation of scientists and satellites devoted to reading the full content of that ancient signal, extracting from its faintest variations the age, the geometry, the composition, and the future of everything. The instruments that did that work are the next part of this story. The problem with measuring the cosmic microwave background from the ground is the same problem that makes a ground-based radio astronomer's life difficult in general. Earth's atmosphere absorbs and emits microwaves. Every instrument pointed at the sky from the surface has to contend with the thermal noise of the air above it, a warm, wet, microwave-absorbing blanket that sits between the telescope and the signal it is trying to read. For the faintest signal in the universe, measured to fractions of a Kelvin, that interference is fatal to precision. The solution was obvious and expensive. Go above the atmosphere of the... And in 1989, NASA did exactly that. The Cosmic Background Explorer, COBE, was the first satellite built specifically to measure the cosmic microwave background from space. It carried two instruments relevant to the thermal story. The first, called FIRAS, the Far Infrared Absolute Spectrophotometer, was designed to measure the spectrum of the background radiation with extraordinary precision. Not just its temperature, but the exact shape of the curve describing how its intensity varies across frequencies. The second instrument, the Differential Microwave Radiometer, was designed to map temperature differences across the sky with enough sensitivity to detect the tiny fluctuations predicted to exist from the earliest moments of the universe. What FIRAS returned was, by the standards of observational science, almost eerie in its perfection. The spectrum of the cosmic microwave background matched the theoretical prediction for a perfect blackbody radiator so precisely that the data points were indistinguishable from the theoretical curve. A blackbody is an idealized object that absorbs all incoming radiation and emits energy in a specific spectral pattern determined entirely by its temperature. The CMB spectrum was the most perfect blackbody ever measured anywhere in nature, a confirmation that the radiation originated from a hot, dense, uniform early universe exactly as the Big Bang model predicted. The temperature was pinned at 2.725 Kelvin. John Mather led the FIRAS instrument team and shared the Nobel Prize in Physics in 2006 for this result. The second result from COBE was in some ways even more significant. George Smoot led the team working with the Differential Microwave Radiometer, and what they found, announced in 1992, were the temperature fluctuations. The 1 part in 100,000 variations in the cosmic microwave background that theory had predicted must exist as the seeds of large-scale structure. The maps were crude by later standards, but the fluctuations were real, and they were there. Smoot shared the 2006 Nobel Prize alongside Mather. Stephen Hawking called it the discovery of the century, possibly of all time. The next generation arrived in 2001. The Wilkinson Microwave Anisotropy Probe, named in honor of Robert Dickey's colleague David Wilkinson, who had devoted his scientific life to measuring the background and died shortly before the satellite launched, observed the cosmic microwave background with roughly 35 times the angular resolution of COBE. Where COBE had produced blurry smears of temperature variation, WMAP produced detailed maps, the baby picture of the universe, as it was quickly called, showing the cosmos at 380,000 years old in sufficient detail to extract precise cosmological parameters. The numbers WMAP returned reshaped the field. The age of the universe, 13.77 billion years. The fraction of the universe's total energy content made up of ordinary matter, the atoms that form stars, planets, and human beings, 4.6%. Dark matter, which interacts gravitationally but not electromagnetically and remains directly undetected, roughly 23%. Dark energy, the mysterious component driving the accelerating expansion of space, approximately 72%. These proportions, extracted from temperature variations in ancient microwave radiation, established the standard cosmological model with a precision that had not previously been possible. The third generation came from Europe. The Planck satellite, operated by the European Space Agency and launched in 2009, observed the cosmic microwave background at 9 separate frequency bands with sensitivity and angular resolution beyond anything WMAP had achieved. Its maps are the most detailed images of the early universe ever produced, temperature fluctuations rendered at angular scales small enough to resolve structures that earlier instruments had only hinted at. Planck refined the age of the universe to 13.798 billion years. It confirmed the spatial geometry of the universe as flat, meaning that parallel lines remain parallel over cosmic distances, and the angles of a triangle sum to exactly 180 degrees. With a precision that rules out significant curvature, it measured the acoustic peaks in the fluctuation spectrum, the imprint of sound waves that oscillated through the primordial plasma before recombination, with enough detail to separate the contributions of ordinary matter and dark matter independently, establishing that dark matter outweighs ordinary matter by roughly 5 to 1. These measurements did something that goes beyond the numbers themselves. They established that the cosmic microwave background, the faint, cold afterglow of the Big Bang, the signal that Penzias and Wilson stumbled onto while trying to eliminate antenna noise, is the single most informative observation in all of cosmology. More information about the structure, age, composition, and geometry of the universe has been extracted from that ancient microwave hiss than from any other source in the history of science. 3 satellites, 30 years of measurement. And what they revealed, more clearly than anything else, is that the universe is not principally made of the things that shine. The atoms, the stars, the galaxies, the warm, luminous exceptions that fill the night sky, amount to less than 5% of everything. The rest is dark, cold, and for the most part invisible. The warm exceptions are extraordinary, but they are still exceptions. And understanding just how exceptional they are requires looking at them against the full scale of what surrounds them. Stars are the most visible fact about the universe. They fill the night sky in every direction. They anchor every galaxy that has ever been observed. They are the source of every photon of visible light that has reached any eye on this planet for the entirety of human history. When people imagine the universe, they imagine stars, furnaces burning in the dark, scattered in their billions across an incomprehensible expanse. It is easy to conclude from this that the universe is, fundamentally, a place full of fire. It is not. Stars are the exceptions. They are extraordinary exceptions, violent, brilliant, and in at least one case the source of all warmth that has ever sustained life on this world. But they are exceptions nonetheless. To understand the true thermal character of the cosmos, you need to understand the stars first, and then you need to understand what surrounds them. The Sun is the star you know best, and it is a useful reference point precisely because it is so thoroughly ordinary. Its surface sits at approximately 5,500 degrees Celsius, hot enough to vaporize any known material on contact, hot enough to emit light across the full visible spectrum and deep into the ultraviolet. Its core reaches approximately 15 million degrees, where the pressure is sufficient to force hydrogen nuclei together through the proton-proton chain, releasing energy in the form of gamma radiation that works its way outward through the solar interior over hundreds of thousands of years before emerging from the surface as the light and heat that reach you. Every second, the Sun converts roughly 4 million tons of matter into pure energy through this process. Not 4 million tons of fuel burned into ash. 4 million tons of mass annihilated, transformed directly into photons through the relationship between energy and mass that Einstein established. That energy radiates outward in every direction, crossing approximately 150 million kilometers of vacuum to reach Earth in about 8 minutes. And the Sun is not a particularly impressive star. Rigel, the blue-white star that marks the left foot of Orion and is visible to the naked eye from almost every inhabited location on Earth, has a surface temperature exceeding 11,000 degrees Celsius, roughly twice the temperature of the Sun's photosphere. Its core runs hundreds of millions of degrees hotter. It is approximately 70 times the mass of the Sun and burns through its fuel with such ferocity that its entire lifespan will span only a few million years. The Sun, by comparison, has been burning steadily for 4.5 billion years and has roughly 5 billion years remaining. Rigel will be dead before the Sun reaches middle age. At the other end of the stellar spectrum sit the red dwarfs, the smallest, coolest, most numerous stars in the universe. Their surface temperatures hover around 3,000 degrees Celsius, roughly half the Sun's. They are so dim that not a single one is visible to the naked eye from Earth, despite the fact that approximately 70% of all stars in the Milky Way belong to this class. They burn their hydrogen so frugally and mix it so thoroughly through their fully convective interiors that the most miserly among them will burn for 10 to 15 trillion years, roughly 1,000 times the current age of the universe. Every red dwarf that has ever ignited is still burning today. Not one has yet exhausted its fuel. Not one has died. Beyond stars, the universe contains thermal environments of even greater extremes in smaller and smaller volumes. When matter falls toward a black hole, it does not fall in quietly. It accumulates in a swirling disk of gas and dust, compressed by gravitational forces so intense that the material heats to temperatures no stable star can sustain. Around stellar mass black holes, objects typically 5 to 20 times the mass of the Sun, the inner regions of these accretion disks reach tens of millions of degrees. Around the supermassive black holes that anchor the centers of galaxies, objects weighing millions or billions of solar masses, the temperatures climb toward hundreds of millions of degrees. The most energetic of these systems, the quasars, an active galactic nuclei powered by the most massive black holes accreting at the highest rates, generate conditions approaching 1 billion degrees across regions that, on cosmic scales, are barely larger than a solar system. These are the hottest sustained thermal environments in the modern universe. And then there are the moments that are not sustained at all. When a massive star exhausts the last of its nuclear fuel and its iron core collapses in a fraction of a second, the temperature at the collapsing core briefly reaches approximately 100 billion degrees. Hotter than any accretion disk, hotter than the interior of any stable star, hotter than the universe has been at any point since the first second after the Big Bang. That temperature exists for milliseconds. The explosion that follows, the supernova, outshines the combined light of every other star in the host galaxy for weeks, before the remnant cools over thousands of years and eventually merges into the cold interstellar medium. The thermal violence is spectacular, and it is entirely fleeting. Here is the question that all of this leads to. These objects, the stars, the accretion disks, the supernovae, are genuinely hot. Genuinely, extraordinarily, almost inconceivably hot by the standards of anything in human experience. But how much of the universe do they actually occupy? How large is the warm fraction of the cosmos measured honestly against the cold that surrounds it? The answer begins with the most basic spatial fact about our stellar neighborhood. The nearest star to the Sun is Proxima Centauri, at a distance of 4.25 light-years, approximately 25 trillion miles. If you shrank the Sun to the size of a ping-pong ball, Proxima Centauri would be another ping-pong ball sitting roughly 720 miles away. Between those two tiny spheres, nothing. 720 miles of empty space, cold, dark, at or near the cosmic baseline temperature, containing not a single other object of any thermal significance. That is not an unusual arrangement. It is the standard spacing of stars in our part of the galaxy. Some regions are denser, particularly toward the galactic center, but even there, stars remain separated by distances that dwarf their own diameters by factors of tens of millions. Scale this up to the galaxy as a whole. The Milky Way contains an estimated 200 to 400 billion stars spread across a disk roughly 100,000 light-years wide. Each star, on average, commands a private volume of roughly 20 to 40 cubic light-years of empty space. The galaxy is almost entirely vacuum. The fraction of its volume occupied by stellar interiors, the hot parts, the parts where nuclear fusion is actually occurring, is so small that expressing it requires scientific notation with a large negative exponent. If you selected a random point inside the Milky Way, the probability of landing inside a star would be vanishingly close to zero. Now scale to the full observable universe. Cosmic voids, vast regions containing almost no galaxies at all, dominate the large-scale structure of space. A typical void spans 100 to 300 million light-years across. The Boötes void, first identified by Robert Kirshner and colleagues in 1981, stretches approximately 330 million light-years and contains fewer than 60 known galaxies in its interior. For comparison, our local group of galaxies packs more than 50 galaxies into a region just 10 million light-years across. The Boötes void is 33 times wider and contains roughly the same number of galaxies, most of them small, dim, and sparsely populated with stars. Scientists estimate that cosmic voids occupy somewhere between 80 and 90% of the total volume of the observable universe. Inside them, no significant energy source heats the local environment above the cosmic microwave background. No stars burn in meaningful numbers. No accretion disks rage. No supernova remnants glow. The temperature is the baseline, 2.725 Kelvin, holding steady across hundreds of millions of light-years, decade after decade, eon after eon, without variation and without exception. The observable universe has a radius of approximately 46.5 billion light-years. Its total volume is enormous beyond any useful comparison. The total volume of all stellar interiors, every core where fusion is actually occurring, in every star, in every galaxy, across all of observable space, amounts to a fraction of that total volume on the order of 10 to the power of -29. That means stellar interiors occupy less than 1/1000th of 1/1000th of 1/1000th of the total volume of space. The rest is cold, not approximately cold, not cold in most places, cold in essentially all places, all the time, by a margin so extreme that the hot fraction does not register as a meaningful quantity against the total. The stars are real. The heat they generate is real. The warmth they deliver to planets near enough to benefit is real, and in at least one case, it has made everything that has ever thought or breathed or grown toward the light possible. But measured as a fraction of the total thermal ledger of the cosmos, all of that warmth, every star, every accretion disk, every supernova, every glowing cloud of ionized gas, is a rounding error. The cold does not compete with the warmth. It simply occupies everything else, and everything else is almost all of it. Understanding this proportion is one thing. Understanding what it means for the specific, fragile, improbable conditions required to produce warmth that can sustain life, that is something else entirely. And it begins with a question that sounds simple. but turns out to have a deeply unsettling answer. What does a world actually need in order to be warm? Before answering that question directly, there is a complication worth confronting, one that seems at first to undermine the argument about cold dominating the universe, but which on closer examination actually deepens it. When astronomers count up the ordinary matter in the universe, the atoms that make up stars, gas clouds, planets, and everything else composed of protons and neutrons, they arrive at a number derived from two independent sources. The pattern of acoustic peaks in the cosmic microwave background tells you precisely how much ordinary matter existed in the early universe. Big Bang nucleosynthesis calculations tell you the same thing from a different angle. Both methods agree. Ordinary matter should constitute roughly 5% of the universe's total energy content. Now go out and count it. Add up the stars in all the galaxies. Add the hot gas detected in galaxy clusters. Add the diffuse gas observed in the space between galaxies. For decades, astronomers looking at the nearby universe could account for only about half of the ordinary matter the early universe should have produced. The rest was missing. Not dark matter, that is a separate accounting entirely. Just ordinary atomic matter, the kind made of protons and neutrons, the kind that can in principle be detected. Half of it was simply not showing up in any survey. This became known as the missing baryon problem, and it occupied cosmologists for the better part of 3 decades. The solution, proposed by Renyu Sen and Jeremiah Ostraker in 1999, was the warm-hot intergalactic medium. As the universe evolved and gravity pulled matter into the filaments and walls of the cosmic web, some of that gas was heated by gravitational shocks. The energy released as material fell into the growing large-scale structure, to temperatures between roughly 100,000 and 10 million Kelvin. This gas sits in the vast filamentary strands connecting galaxy clusters, too diffuse to form stars, too hot to emit much visible light, and too spread out to be easily detected by conventional means. Theoretical models suggested it could account for the missing 40 to 50% of all ordinary matter in the universe. Direct observational confirmation came in 2018, when Fabrizio Nicastro and colleagues used X-ray spectroscopy to detect absorption features in the light of a distant quasar caused by oxygen ions in the warm-hot intergalactic medium along the line of sight. The missing baryons were found. They were in the filaments, heated to temperatures that, by any ordinary reckoning, qualify as hot. And here is where precision of language becomes essential. Because the warm-hot intergalactic medium is technically hot in the sense that its particles move at velocities corresponding to millions of degrees. But temperature, remember, is an intensive property. It describes the state of whatever matter is present, not the total amount of energy in a given volume. The warm-hot intergalactic medium is also extraordinarily sparse. The density of this gas is so low, just a handful of particles per cubic meter in the densest filaments, far less in most of the volume, that a spacecraft traveling through it would feel nothing whatsoever. Think about what that means. You could float in a region where the gas temperature technically reads 1 million degrees, and your body would still radiate heat outward and cool. The hot particles would almost never collide with you. Their individual kinetic energies are real, but there are so few of them that the total thermal energy they deposit on any surface per unit time is negligible. The gas is hot in the same way that a single spark is hot, technically accurate and thermally irrelevant at any practical scale. This is the distinction between temperature and thermal energy density, and it is one of the most important ideas in understanding the true thermal character of the cosmos. A gas can register millions of degrees while contributing nothing meaningful to the warmth of anything within it. The universe can contain regions technically described as hot while remaining, in every sense that matters physically, cold. The warm-hot intergalactic medium does not change the thermal accounting. It confirms that ordinary matter has found its way into the cosmic web, which is valuable and important, but it does not heat the cosmos. The filaments are hot by one definition and cold by every practical one, which brings the question of cold back into focus from a different direction entirely. Because while the universe is cold is mostly a consequence of scale and distribution, human beings have spent the last century trying to reproduce something like cosmic cold deliberately, to manufacture, in a laboratory, temperatures that the natural universe almost never achieves outside of deep space. The quest to reach absolute zero is one of the strangest stories in the history of physics. The challenge is this: every method of cooling an object works by transferring its thermal energy somewhere else, into a colder reservoir, into evaporating fluid, into outgoing radiation. The lower the temperature you are trying to achieve, the smaller the energy differences you are working with, and the harder it becomes to extract what remains. Each step toward absolute zero requires a more refined technique than the one before, and the floor recedes as you approach it, exactly as the third law of thermodynamics guarantees it must. In the early 20th century, reaching liquid helium temperatures, 4.2 Kelvin, was considered a feat of extreme technical difficulty. The Dutch physicist Heike Kamerlingh-Onnes first liquefied helium in 1908, a result that required decades of prior work on cryogenic technique and earned him the Nobel Prize in Physics in 1913. Liquid helium opened the door to the study of superconductivity and superfluidity, phenomena that only emerge when thermal energy is reduced to the point where quantum effects dominate the behavior of matter. Getting below liquid helium required new approaches entirely. Pumping on liquid helium to lower its vapor pressure can bring temperatures down to about 1 Kelvin. Dilution refrigerators, devices that exploit the mixing properties of two isotopes of helium, can reach temperatures of a few thousandths of a Kelvin, colder than anything the natural universe achieves outside of a few specialized astrophysical environments. But the most dramatic advance came from a completely different direction. In the 1980s and 90s, physicists developed techniques to cool not bulk matter, but individual atoms, using light itself as a refrigerant. Laser cooling exploits the Doppler effect. An atom moving toward a laser beam absorbs a photon and recoils slightly, slowing down. An atom moving away from the beam sees the photon Doppler shifted out of resonance and does not absorb it. By carefully tuning the laser frequency and directing beams from multiple directions simultaneously, it is possible to slow atoms from every direction at once, reducing their average kinetic energy to the point where they are barely moving. The technique was developed independently by several groups in the 1980s, and Stephen Chu, Claude Cohen-Tanuji, and William Phillips shared the Nobel Prize in Physics in 1997 for their contributions to it. Laser cooling alone can reach temperatures of millionths of a Kelvin. To go further, physicists turn to evaporative cooling, allowing the fastest, hottest atoms in a magnetically trapped cloud to escape, while the remaining atoms rethermalize at a lower temperature. The same principle by which a cup of hot tea cools as the most energetic molecules evaporate from the surface applied to a cloud of atoms at temperatures already colder than anything in the natural universe. Using this combination of techniques, Eric Cornell and Carl Wieman at JILA in Boulder, Colorado, succeeded in 1995 in producing a Bose-Einstein condensate, a state of matter predicted by Satyendra Nath Bose and Albert Einstein in 1924 and 1925, in which atoms cooled to extreme proximity to absolute zero lose their individual identities and begin to behave as a single quantum entity. The temperature at which Cornell and Wieman achieved this was approximately 170 billionths of a Kelvin above absolute zero. Wolfgang Ketteler at MIT independently achieved condensation with a different atomic species shortly after. All three shared the Nobel Prize in Physics in 2001. Subsequent experiments have pushed further still. Temperatures of less than 1 billionth of a Kelvin have been produced in specialist laboratories. The floor has been approached to within distances that make the gap between the coldest laboratory achievement and absolute zero smaller than the gap between absolute zero and the cosmic microwave background temperature. And still absolute zero holds. Still the third law holds. Still every atom retains its last irreducible quantum flicker of zero-point energy, unreachable by any physical process. The coldest things that have ever existed in the universe are not out in deep space. They are in laboratories on the surface of a warm planet, constructed with enormous effort and expense, maintained for fractions of a second before warming back up. The universe does not naturally produce these temperatures. It approaches them. The cosmic microwave background sits closer to absolute zero than liquid helium does. But the engineered cold of a Bose-Einstein condensate laboratory goes further than nature has managed anywhere we can observe. It is a strange inversion. The most extreme cold ever achieved exists not in the void between galaxies, but in a room, inside equipment, maintained by people who spent careers learning how to get there. The universe makes cold effortlessly and everywhere. We make it with difficulty and only for an instant. But the universe cannot quite reach the floor it sets for itself, and neither, for all our ingenuity, can we. So, what does a world actually need in order to be warm? The question sounds as though it has a short answer. A star nearby, enough distance to avoid being scorched, something to hold an atmosphere, the basics. Most people who think about it for a moment arrive at something like that list and feel reasonably satisfied. The real list is longer, much longer, and each item on it is not merely a helpful condition, but a necessary one. A link in a chain where removing any single link produces a world that is frozen solid, or boiled dry, or scoured of its atmosphere, or geologically dead, or any of a dozen other variations on the theme of uninhabitable. The warmth you experience on the surface of this planet is not a simple consequence of being at the right distance from a star. It is the end product of a chain of physical requirements, so specific, so interdependent, and so contingent on how things happen to unfold over billions of years that it deserves to be examined with some care. Start with the star. Not every star will do. The Sun is a G-type main sequence star, a yellow dwarf of middling mass, burning hydrogen in its core at a rate that has kept its luminosity remarkably stable over 4.5 billion years. That stability matters. Life on Earth did not appear overnight. The transition from chemistry to biology, from simple single-celled organisms to the first complex multicellular life, took billions of years of continuous, patient evolution. A star that exhausted its fuel in a few 100 million years, as the most massive stars do, would not allow that process time to unfold. The star had to burn steadily, at roughly the right luminosity, for long enough. The Sun has done this. Not every star could. Orbital distance is the next requirement, and it is one that most people have at least heard of. The habitable zone around a star, the band of orbital distances within which a rocky planet can maintain liquid water on its surface, is relatively narrow. For the Sun, it spans roughly from about 95% of Earth's current orbital distance to perhaps 1.5 to 1.7 times that distance, depending on the model used and the assumptions made about atmospheric composition. Earth sits comfortably within it. Mars sits near its outer edge. Venus sits just inside or just outside its inner edge, depending on how the zone is defined. Here is the thing about that zone. Its width, expressed as a fraction of the distance from the Sun to the nearest star, is less than 1/1,000,000,000 of 1%. It is a thin ring of orbital real estate in an enormously vast solar system, itself a small system among hundreds of billions in the Milky Way, itself one galaxy among trillions. The zone exists. Earth occupies it. But its narrowness is a useful reminder of how precisely things need to line up. Orbital distance, however, is not enough. A planet at the right distance with no atmosphere would be the Moon. A world of killing extremes, averaging well below freezing even at the right distance from the Sun, with no moderation between the heat of day and the cold of night. The atmosphere is not an optional extra, it is load-bearing. Earth's atmosphere does several things simultaneously that are each essential. It provides the greenhouse effect, primarily through water vapor and carbon dioxide, which raises the average surface temperature by approximately 33 degrees Celsius above what it would be on a bare rock at the same orbital distance. Without this effect, Earth's average surface temperature would sit around -18 degrees Celsius, and the oceans would be frozen solid. The atmosphere also redistributes heat through convection and circulation, moderating the temperature difference between equator and poles, between day and night, between the seasons. Remove it, and the surface becomes the moon. But maintaining an atmosphere requires planetary mass in the right range. Too little mass, like Mars, and the gravitational grip is insufficient to retain lighter gases against the pressure of the solar wind and the heat of the upper atmosphere. Mars almost certainly had a denser atmosphere in its youth, and geological evidence suggests it may have supported liquid water at its surface for hundreds of millions of years. Then something changed. That something was the magnetic field. Mars lost its global magnetic field roughly 4 billion years ago as its interior cooled and its liquid iron core solidified, shutting down the dynamo that generates a magnetosphere. Without a magnetic field, the solar wind, a continuous stream of charged particles from the sun, struck the upper atmosphere directly, stripping it away particle by particle over hundreds of millions of years. Mars's atmosphere today is roughly 1% as dense as Earth's, too thin to provide meaningful greenhouse warming, too thin to support liquid water at the surface. The average surface temperature of Mars is approximately minus 60 degrees Celsius. A magnetic field, then, is not a luxury. It is a condition. Earth's magnetic field is generated by convection in the liquid iron outer core, a consequence of the planet having the right internal heat budget, the right composition, and the right balance between initial formation heat and radioactive decay to keep a portion of the iron interior liquid for billions of years. Change the planet's size, its composition, or its distance from the sun, and that balance shifts. A slightly smaller planet might have cooled faster and lost its dynamo earlier, as Mars did. A slightly different composition might not have produced the right density, layering for an iron core to form at all. Then there is the carbonate-silicate cycle, the long-term thermostat that has kept Earth's surface temperature within a habitable range through ice ages, volcanic cataclysms, and asteroid impacts over 4 billion years. The cycle works as follows. Volcanoes continuously emit carbon dioxide into the atmosphere. Rainfall absorbs that carbon dioxide, forming weak carbonic acid, which weathers silicate rocks and carries the resulting calcium carbonate to the ocean, where it eventually gets incorporated into sediment and subducted back into the mantle. The rate of weathering depends on temperature. A warmer surface speeds it up, pulling more carbon dioxide out of the atmosphere and cooling the planet. A colder surface slows it down, allowing volcanic emissions to accumulate and warm things back up. This feedback loop has operated continuously for billions of years, making corrections automatically whenever the climate drifts too far in either direction. It requires active plate tectonics to work. The geological machinery that drives subduction and volcanism has to be running. A geologically dead planet cannot operate the thermostat. James Casting at Penn State University spent decades working out the boundaries of the habitable zone and the conditions required to maintain it over geological time. The picture that emerged from his work, and from the work of researchers building on it, is of habitability as a system, not a single condition, but an interlocking set of requirements that must all be satisfied simultaneously and maintained over timescales of billions of years. Each requirement, taken alone, might seem manageable. Together, they describe a target so precise that hitting it by chance seems almost implausible. And yet, here we are. But here is where the story takes a turn, that most treatments of habitability skip entirely. Even on Earth, with all of those conditions satisfied, warmth has not been a permanent or guaranteed feature. It has wobbled, dramatically. And the most dramatic wobble of all came close, at least twice, to ending the story before it had properly begun. In the 1990s, a geologist named Paul Hoffman began assembling geological evidence from ancient rocks on every continent. Glacial deposits, the distinctive scratching patterns left by moving ice, specific chemical signatures preserved in sediment, and the picture they collectively painted was extraordinary. Roughly 700 million years ago, during a period called the Cryogenian, glaciers advanced from the poles all the way to the equator. Ice sheets reached tropical latitudes. The entire surface of the Earth, or very nearly all of it, was covered in ice and snow. The surface temperature at the equator may have dropped to minus 50 degrees Celsius. The oceans, if not frozen solid to their depths, were sealed beneath kilometers of ice. The planet had entered a state called Snowball Earth. Carl Sagan and George Mullen had identified in 1972 the physics that makes this state dangerous to escape. Ice and snow are highly reflective. They bounce incoming solar radiation back into space rather than absorbing it. The more ice there is, the more sunlight is reflected. The colder it gets, the more ice forms. This is called the ice albedo feedback, and it is self-reinforcing. Once it takes hold strongly enough, it can drive the planet to a fully glaciated state and keep it there. Sagan and Mullen had framed this as the faint young sun paradox. How did early Earth, receiving less solar energy than today, avoid freezing entirely? But the same physics explains how snowball Earth events could have locked the planet into a frozen equilibrium. How did Earth escape? The answer is the carbonate silicate thermostat, operating in extreme conditions. Under the ice, the volcanoes kept emitting. The subduction kept cycling. But the ice suppressed weathering almost completely. There was no liquid water at the surface to react with silicate rocks and remove carbon dioxide from the atmosphere. So carbon dioxide accumulated. For millions of years, carbon dioxide poured into the atmosphere with nothing removing it. The greenhouse effect built slowly, invisibly, under the ice, until it finally overcame the ice albedo feedback. The ice began to melt. As it melted, the reflectivity dropped, more sunlight was absorbed, and the warming accelerated. The exit from Snowball Earth may have been catastrophic in its speed, temperatures swinging from deep freeze to perhaps 50 degrees Celsius or warmer in a geological instant, as hundreds of millions of years of accumulated carbon dioxide were suddenly released into a warming world. This happened at least twice, possibly more. The evidence is in the rocks, and it is unambiguous. The implications are worth sitting with. Earth had all the right conditions, the right star, the right orbit, the right atmosphere, the right magnetic field, the geological machinery, and it still nearly froze completely, twice in the last billion years. Warmth on a habitable world is not just hard to establish, it is hard to keep. And the story of how Earth was warm enough to have life in the first place, billions of years before those snowball events, is strange in its own right. Because the sun, in Earth's early history, was not the sun you know. 4 billion years ago, the sun was roughly 70% as luminous as it is today. Stars like the sun grow gradually brighter over their main sequence lifetimes, as hydrogen fusion in the core slowly changes its chemical composition, increasing the core's density and driving up the rate of energy generation. The sun you see in the sky is meaningfully brighter than the sun that shone on the early Earth, and the sun that will shine on the Earth in a billion years will be meaningfully brighter still. This creates a problem with no fully settled solution. In 1972, Carl Sagan and George Mullen published a paper laying out the contradiction precisely. Standard climate models, applied to the early Earth with a sun 30% less luminous than today, predict a planet frozen from pole to pole for its first 2 billion years. The physics is straightforward. Less energy arriving from the sun means a lower equilibrium temperature, and at the distances and atmospheric conditions assumed for the early Earth, the equilibrium falls below the freezing point of water. The oceans should have been solid ice. They were not. The geological record is unambiguous on this point. Sedimentary rocks formed in liquid water exist from as far back as 4.4 billion years ago. Ancient river channels, chemical signatures of liquid oceans, and the fossil evidence of life itself. Microbial life existed on Earth at least 3.5 billion years ago, and possibly significantly earlier. All testify to a planet that was not frozen. Liquid water was present on Earth's surface during precisely the period when the sun was too dim, according to standard models, to keep it liquid. Something kept the early Earth warm when the sun could not. The question of what that something was is called the faint young sun paradox, and it remains one of the genuinely unresolved problems in planetary science. The most widely discussed solution involves greenhouse gases. If the early atmosphere contained significantly higher concentrations of carbon dioxide, methane, or other greenhouse gases than the modern atmosphere, the enhanced greenhouse effect could have compensated for the weaker solar input. There is geological evidence supporting elevated carbon dioxide levels in the early atmosphere, and some models suggest methane produced by early microbial life may have contributed substantially. Raymond Wordsworth and Robin Pierre Humbert proposed in 2013 that hydrogen, a more potent greenhouse gas than had previously been appreciated when combined with nitrogen, may have played a significant role, particularly if the early Earth released more hydrogen through volcanic outgassing than modern analogies suggest. None of these solutions has achieved consensus. Each one requires assumptions about the early atmosphere that cannot be directly verified from the geological record. The faint young sun paradox has been studied for 50 years, and the field has not yet converged on a single explanation. It is possible that multiple mechanisms contributed simultaneously. It is possible that the answer involves a combination of factors: slightly higher greenhouse gas concentrations, slightly different cloud cover and albedo, a somewhat different distribution of continents affecting ocean circulation, none of which alone would be sufficient, but which together tip the balance toward liquid water. What the paradox illustrates above all is that the thermal history of even a well-positioned, well-equipped habitable world is more complicated and more contingent than it looks. The warmth was not guaranteed. It required conditions that happened to be in place, maintained by processes that happened to keep running, against a background of solar input that was insufficient on its own. Earth was warm in its youth because something filled the gap. We do not yet know with confidence what that something was. But before moving on from warmth without adequate solar input, there is a category of environment that the conventional habitable zone concept misses entirely, and which may turn out to be among the most important thermal environments in the solar system. Not every warm place in the universe gets its heat from a star. Consider Io, the innermost of Jupiter's large moons. It sits at approximately 5 astronomical units from the Sun, well beyond the frost line, in a region of the solar system where direct solar heating is far too weak to maintain liquid water at the surface or anywhere near it. Io's surface temperature averages around -130 degrees Celsius in the shade, and yet Io is the most volcanically active body in the solar system. Its surface is covered in sulfur compounds and silicate lava fields. Volcanic plumes erupt hundreds of kilometers into space. Hotspots on its surface reach temperatures of over 1600 degrees Celsius. The heat does not come from the sun, it comes from inside, from the continuous gravitational kneading of Io's interior by Jupiter's enormous tidal forces, amplified by the orbital resonance Io shares with its neighboring moons Europa and Ganymede. As Io orbits Jupiter in an orbit kept slightly elliptical by these gravitational interactions, the tidal bulge on its surface rises and falls. The repeated flexing generates heat through friction deep in the moon's interior, keeping it geologically alive in a region where direct solar energy would leave it frozen and dead. Tidal heating is a different kind of warmth. It is entirely independent of where you are relative to a star. It depends on gravity, on orbital geometry, and on the internal properties of the body being heated. Now consider Enceladus, a small moon of Saturn, just 500 kilometers across, orbiting at roughly 10 astronomical units from the Sun. Saturn's solar input is roughly 90 times weaker than Earth's. By every conventional measure, Enceladus should be a frozen rock. Its surface is, in fact, covered in ice, with a surface temperature of approximately -200 degrees Celsius. But in 2005, the Cassini spacecraft detected something extraordinary at the moon's south pole. Jets of water vapor, ice particles, organic molecules, and molecular hydrogen were erupting through cracks in the ice, geysers fed by a subsurface ocean of liquid water that exists, warm enough to stay liquid beneath kilometers of ice. The heat source is tidal friction from Saturn. The ocean has been liquid for potentially hundreds of millions of years. The presence of molecular hydrogen in the plumes indicates ongoing hydrothermal reactions between the water and the rocky seafloor. The same general type of chemical environment found at hydrothermal vents on Earth's ocean floors, which support entire ecosystems without any input of solar energy. Europa, Jupiter's ice-covered moon, almost certainly harbors a similar subsurface ocean, possibly larger in total volume than all of Earth's oceans combined, kept liquid by tidal heating from Jupiter. Ganymede, Jupiter's largest moon, may have one as well. These are not marginal candidates. They are among the most seriously considered potential locations for life in the solar system. What this means for the question of warmth is significant. The habitable zone, the orbital band where stellar radiation can maintain liquid surface water, is not the only place where liquid water can exist. Tidal heating can maintain it in darkness, at enormous distances from any star, in bodies far too small to retain their own radiogenic heat for geological timescales. The range of potentially warm environments in the universe may be considerably larger than the narrow stellar habitable zones suggest. NASA's Europa Clipper mission is on its way to Jupiter's system. The European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, is also en route. Both are designed to characterize these subsurface ocean environments in detail, to measure the depth and chemistry of the water, and to assess whether the conditions exist that might support life. The answers will arrive in the coming decades. But while those questions remain open, the thermal future of the system that hosts all of these worlds is not open at all. The Sun's future is written in the physics of stellar evolution, and it is a story of warmth that becomes first too much and then nothing. The Sun has burned hydrogen in its core for approximately 4.5 billion years. It has roughly 5 billion years of stable burning remaining. That is reassuring in the immediate sense. 5 billion years is a very long time. But the stability is not permanent, and before the final exhaustion arrives, something more immediately relevant to life on Earth will happen first. As the Sun continues to brighten over its remaining main sequence lifetime, its increasing luminosity will eventually push Earth's surface temperature past the threshold where the oceans can remain stable. In approximately 1 billion years, a number that sounds comfortably distant, but represents less than a quarter of the time life has already existed on this planet, solar output will have increased enough to trigger a runaway greenhouse effect. Water vapor will accumulate in the upper atmosphere, accelerating warming further, and the oceans will eventually evaporate. Life on Earth's surface will become impossible long before the Sun reaches old age. When the Sun does exhaust its core hydrogen, roughly 5 billion years from now, it will swell into a red giant, expanding its outer layers outward past the orbit of Venus, and possibly engulfing Earth entirely. The surface temperature of the red giant Sun will be lower than today's, but its vastly larger size will mean that the heat delivered to the inner solar system increases enormously. Whatever remains of the inner planets at that point will be scorched into bare rock at best. The outer layers will eventually be expelled as a planetary nebula. The core will contract under gravity into a white dwarf, an object roughly the size of Earth, composed of the compressed remnant of the solar interior, initially glowing hot with residual heat, but producing no new energy of any kind. It will begin to cool from that moment forward, radiating its stored heat into the void, fading gradually from white to yellow to red to infrared over timescales measured in billions of years. The Sun's gift of warmth, extended across 5 billion more years of stable burning, is finite. It always was, and what follows it, for this solar system and for every other, is the long quiet dark. How long that dark lasts, and what it contains, is where the story goes now. The era of stars, the period in cosmic history during which nuclear fusion lights the universe from within, is not permanent. It is not even, by the standards of deep time, particularly long. The Stelliferous era, as Fred Adams and Gregory Loughlin named it in their 1997 survey of the long-term fate of astrophysical objects, spans roughly from the formation of the first stars a few 100 million years after the Big Bang, to the extinction of the last red dwarfs, perhaps 100 trillion years from now. 100 trillion years sounds like an incomprehensible duration. by the standards of what follows it, it is a brief opening act. Red dwarfs will be the final stars. Their frugality is their longevity, burning so slowly, mixing their fuel so thoroughly, that the most miserly among them will still be fusing hydrogen when the universe is 1,000 times its current age. As the raw material for new star formation, cold molecular hydrogen accumulated in galactic disks is gradually consumed over the coming hundreds of billions of years, the rate of new star births will decline. Eventually, it will reach zero. The last star to ignite will be a red dwarf, burning dimly and alone in a universe that has grown dark around it. When it finally exhausts its supply, there will be no new ignition to follow it. The lights will go out, not dramatically, not all at once. One by one, over trillions of years, the last stars will cool and fade, each one a white dwarf at the end, a cooling ember radiating its residual heat into an expanding void, with no process to replenish what it loses. What follows the stelliferous era is the degenerate era, a period dominated not by burning stars, but by their cooling corpses. White dwarfs, neutron stars, and the black holes that have accumulated mass across billions of years of stellar death. This era will last far longer than the age of stars it follows. White dwarfs radiate their heat slowly. Over timescales of quadrillions of years, they will fade from the temperatures of living stars through every color of the cooling sequence, eventually reaching temperatures indistinguishable from the cosmic background. Each one is a private, patient rehearsal of the same process that has been cooling the universe since the beginning. A concentrated pocket of energy slowly dissipating into the void that surrounds it. During all of this, black holes will grow, merging, accreting whatever diffuse matter remains in their vicinity, accumulating mass over timescales so vast that the entire history of stellar evolution will eventually seem like a brief prelude. And then, slowly, over timescales that reduce every previous number in this story to a rounding error, they will begin to die. In 1975, Stephen Hawking derived a theoretical result that remains one of the most remarkable in the history of physics. Black holes, he showed, are not perfectly black. Quantum effects near the event horizon cause the emission of thermal radiation, a faint, continuous leak of energy from the region just outside the point of no return, driven by the behavior of virtual particle pairs in the curved space-time near the horizon. This radiation carries away energy. Over time, the black hole loses mass. Given enough time, an almost incomprehensibly long time, it evaporates completely, ending in a brief burst of high-energy radiation. For a stellar mass black hole of roughly 10 solar masses, the evaporation time is approximately 10 to the power of 67 years, a number with 67 digits. The current age of the universe is approximately 10 to the power of 10 years. The evaporation time of a stellar black hole is therefore roughly 10 to the power of 57 times the current age of the universe, a ratio so extreme that writing it in words serves no useful purpose. For the supermassive black holes at the centers of galaxies, objects weighing billions of solar masses, the evaporation times run to approximately 10 to the power of 99 years. After the last of these has evaporated in a faint final flash, the universe will contain nothing but dispersed photons, electrons, positrons, and neutrinos, particles drifting apart in an expanding void that grows colder with every passing moment, with nothing left to generate new energy of any kind. This is the dark era. It has no end in any conventional sense. It is simply the universe's final state, cold, dark, expanding, and silent, approached asymptotically as the last traces of structure and energy dissipate into the void. There is genuine uncertainty about some of this. Hawking radiation has not been directly observed. The theoretical framework from which it derives is solid, but the timescales involved make experimental confirmation essentially impossible with any technology imaginable. Some alternative cosmological models propose different endings. If dark energy increases in strength over time, the universe might end in a big rip, space-time itself torn apart by accelerating expansion before the black holes have time to evaporate. The nature of dark energy remains one of the deepest unsolved problems in physics, and what it will do over cosmic time is genuinely unknown. The heat death scenario is the best current answer. It is not a certainty. What is certain is the direction. The universe moves toward thermal equilibrium. It always has. Energy concentrations dissipate. Temperature differences smooth out. Warm pockets in a cold cosmos cool toward the background. The second law of thermodynamics does not admit exceptions. It permits local, temporary concentrations of energy, stars, living organisms, the warmth of a planetary surface, but it guarantees that each one is temporary. Every flame burns down. Now step back, hold the full picture. The universe began in a state of heat so extreme that the concept of temperature as we normally use it barely applies. It has been cooling for nearly 14 billion years. The expansion of space stretched the primordial fire into the 2.725 Kelvin whisper that fills all of space today. Stars have burned as local exceptions, brilliant, temporary, essential, across a cosmic volume so vast that they occupy a fraction approaching zero of its total. Voids dominate the large-scale structure. Cold dominates the thermal budget. The era of stars, which will last 100 trillion years, amounts to a vanishing sliver of the total timeline if you count to the evaporation of the last black hole. Against all of that, consider this planet. Earth sits in the habitable zone of a stable G-type star. Its mass is sufficient to retain an atmosphere. Its iron core generates a magnetic field. Its geological activity drives the carbonate silicate thermostat. Its axial tilt is stabilized by a large moon. Its outer solar system contains a gas giant that has deflected a meaningful fraction of the cometary and asteroidal material that would otherwise have bombarded the inner planets at sterilizing frequency. Its atmosphere contains precisely the mix of greenhouse gases needed to raise the average surface temperature 33 degrees above what a bare rock at this distance would achieve. Every one of these conditions had to be in place simultaneously and had to remain in place for the 4 billion years of biological evolution that produced the capacity to ask questions about the universe at all. The Kepler mission, which surveyed the brightness variations of over 150,000 stars for 4 years, gave us the first statistical picture of how common Earth-sized planets in habitable zones might be. The estimates suggest that perhaps 1 in 5 Sun-like stars hosts a rocky planet in the habitable zone. Across hundreds of billions of stars in the Milky Way alone, that suggests billions of candidates. The James Webb Space Telescope is now performing atmospheric characterization of some of these worlds, reading the chemical fingerprints of their atmospheres in the starlight that filters through them as they transit their host stars. In the coming decades, we may find atmospheres that hint at the presence of surface liquid water or chemical signatures that no purely geological process produces. We do not yet know whether any of those worlds are warm in the way Earth is warm, whether any of them have threaded every needle, whether any of them have run the chain of requirements without a broken link long enough for anything to notice. That question is still open, but here is what is not open. The universe is cold, not in some limited or qualified sense. Overwhelmingly, fundamentally, pervasively cold, across more than 80% of its volume by the most conservative estimates, and at the baseline temperature of 2.725 Kelvin across the emptiest regions that stretch for hundreds of millions of light years without interruption. The hot parts are real and extraordinary, but they are genuinely exceptional, statistically negligible against the total, temporary against the full span of time, each one a local resistance to a universal trend that will outlast them all. You are warm right now. The air around you sits within the narrow thermal range that permits the chemistry of life. The planet beneath you has maintained that range for 4 billion years through a combination of conditions that required the entire history of this solar system to assemble. The star above you has been burning steadily for 4.5 billion years and will burn for 5 billion more. None of it was guaranteed. None of it is permanent. All of it is, in the full context of what the universe is and what it will become, extraordinarily rare. The cold is not coming for you. It does not need to. It is already everywhere else. in the voids between the galaxies, in the darkness between the stars, in the slow cooling of a universe that was born in fire and has been moving towards silence ever since. It surrounds everything that has ever burned or breathed or grown toward the light, and it will be there long after the last star has cooled and the last black hole has faded and the last photon has stretched to a wavelength with no energy left to carry. The warmth is here, right now. It is real, and it is remarkable, and it will not last forever. That is not a reason for despair. It is a reason to look at it clearly and to understand finally what it actually is. It is the exception,